Okay, so we're going to talk about validation and cross-validation, and we'll use an example data set to show this. So I won't read through all this, but what we're going to do is split our sample data set. So we're going to use one data set to do the validation, and we're going to split our data set into a training group, which we're going to use to develop the model, and a testing group, or sometimes called a holdout group, to test the model to see how well we can predict out of sample data. So we're going to use part of our data to develop the model and part of our data to test the model. And we're going to compare the test MSE, or as I say here, it's more accurately generally called the prediction error, from different models with different complexities to try to figure out which one seems the most generalizable. We can also use model validation as a variable selection technique. Suppose that through different techniques, through say forward selection, or maybe using all possible regressions with the adjusted R squared, or different approaches that we talked about in class activities 8 and 9, we might find a handful of good models. We can then use these model validation techniques to figure out which one has the lowest test MSE, and then use that for our final model. So this is also a good approach for selecting between competing models. We're going to talk about there's lots of different ways to do model validation. We're going to talk about two cases. The first one we're going to talk about is sometimes called split halves validation or cross validation. And this is where we only do it once. So we only have one validation set of data. So hence I'm calling this validation rather than cross validation. But we simply randomly separate the data into two data sets. This is split the data in half, but we could also use something like a 70-30 split or an 80-20 split. Generally you want more data to build the model, to train the model, than you do to test the model. So the training data set might be 70 and the training data or testing data might be 30% of the data. I'm going to call these just sets 1 and 2, S1 and S2. We're going to create the model using the data in S1. That's our training data. And we're going to use that to perform variable selection, test assumptions, do everything that we normally do to build our model. But then once we fit that model, we're going to take the fitted model to predict the responses of the observations in S2. So for every row in S2, we're going to use our model to calculate a Y hat for the data and the testing data. And then we're going to calculate the test MSE to estimate the prediction error in the model. So this is kind of the key thing here, is you don't touch the test data. We don't touch the test data until after you've formulated and built the model using the training data. Okay? So let's do an example of this. We're going to use the first year GPA data again from class activity 9. So we use the first year GPA data and load the data into SAS. We could use proc import, or we could copy and paste. I've already loaded the data in here, and I've just used the copy and paste approach to loading the data. So I already have the data in there. Okay. And actually, let me go ahead and run this again, or even better, we can say proc contents. Proc contents is a way for you to look at the nature of your data. I think I called this GPA. Is that what I called this data set? Yes, data GPA. So with proc contents, we can look at to see what's in our data. And this tells us that there are 219 observations. So there are 219 rows in our data set, and there are 10 variables in the data set. Okay? Keeping in mind though, that some of these variables, actually I think we'll end up using almost all these variables. We have GPA, which is what we're trying to predict. That's first year GPA, high school GPA, SAT, verbal, SAT, math, male students. HU is the number of humanities credits that they took as the first year. Social science credits, whether they're first generation students, that's a dummy variable. It's already coded 0, 1, so we don't have to do anything with it. Whether they're white as compared to other races, again, that's already coded 0, 1. And whether they come from a college-bound school, I guess where a higher proportion of students go to school or go to college from their school. Again, we already have those dummy variables in the data, so we don't have to do anything with those. And so we first want to predict first year GPA using the variables. Let me switch back to this, sorry. So we want to create a model using the variables high school GPA, number of credits in the humanities, or HU, and race, which is our dummy variable for white. It's equal to 1 if white, 0 if other. So create a matrix of scatter plots for these 4 variables. What sorts of relationships do you see? I think I already have it here. No, I don't have it here already. So let me go ahead and do that. So we can do proc SG scatter, matrix GPA, high school GPA, humanities, and what's the other one? White. So white's a 0, 1 variable, but you'll see we can also look at that in terms of a scatter plot. So here's our matrix of scatter plots. My computer is running very slowly here. And if we're mostly interested in the scatter plots up here at the top that have GPA on the y-axis, because that's our response variable. And what do we notice? Well, for high school GPA, there does seem to be somewhat of a linear relationship. For number of humanities, again, there's certainly a positive correlation going on there. I don't know how linear it is, but definitely a positive correlation. And then for white versus non-white, you can see a slight shift upwards here in the GPA points for those who have a 1 for white compared to those who have a 0 for white. So what sorts of relationships do we see? See, possibly linear relationships between GPA, that's the first year college GPA, and high school GPA, and number of humanities. Also looks like GPA is higher for white than non-white students. And that's not a general statement, that's just on average. Looks like maybe there's we can look at that again, maybe there's a shift up. So I'm looking at the points for the non-white students might be shifted down a little bit compared to the points for the white students. So here's just another way that you can look at a binary variable, the 0, 1 variable, relative to a quantitative variable. We can still do a scatter plot for those, and it can be informative. So now what we're going to do is we're going to actually simultaneously make 2 new data sets based on the GPA data set. We're going to create a training data set and a testing data set. So the way I'm going to do this is I'm going to first create a variable u that's just going to be a randomly generated uniform variable between 0 and 1. So I say, do you remember what the cost stream init function does? And you may not have seen this before if you didn't use the reverse regressions class assignment that I made optional. But what call stream init, call stream init sets what we call the seed for STS's random number generator. You may or may not know this, but computers don't actually generate random numbers. The random numbers computed by generators are actually called pseudo-random number generators. And they're actually mathematically derived, and it depends on the seed that we're going to set. But the numbers that come out are close to being random. They're reasonable approximations to randomness. But so SAS uses this seed to actually calculate the first random or pseudo-random number. And that's the way all random number generators work in computers, is you generally have to give it a seed, and then it goes from there. So here's how we're going to do this. We're going to simultaneously create two data sets, and this is how you can do it. You can specify both names in your data step. So we're going to simultaneously create two data sets, training and testing. And we're going to randomly populate these data sets. Set GPA just brings in the GPA data set. So this brings in existing data set that we've already created. I already loaded the data up above, so GPA exists. Call stream init sets my seed. And what that will do is every time I run this program, it will give me the same random numbers. And you might wonder why you want to do that. And the reason I want to do that is because if I want to reproduce my results, I want to be able to create the same set of random numbers. If you want to change the random numbers, you can change the seed. And I pick fun numbers for my seeds. So if you've ever heard 8675309 before, you can look up Jenny or call Jenny, and that will that's from a 1980s song. U equals random uniform. This will generate uniform pseudo-random, I'm going to say random in quotes, random numbers between 0 and 1. So for every record in your data set, it will create a random number between 0 and 1. And I'm just going to say if U is less than 0.5, then we're going to put that observation in the training data set. If it's bigger than 0.5, we're going to put it in the testing data set. So this is creating our split halves. And they won't be exactly halves because we don't expect, this is a random split. So we don't necessarily expect exactly half to go in training and exactly half to go in testing, but it should be pretty close. Okay, so I already have these data loaded into my SAS, or this code loaded into my SAS. So here's the exact same code. And oh, here's my scatter plot from above. I don't need that anymore. And here I'm going to split the data. If I run this code, look at the log file, you can see that 118 observations went into training and 101 went into testing. You see the dataset training has 118 observations, the dataset testing has 101 observations. So 118 went into training, 111 went into testing. With my seed, it won't always happen like that, okay? If you pick a different seed to start your random numbers, you'll get a different split, but it should be about half and half. So now I want to run the code to fit a model with GPA as a response and high school GPA, HU, and weight as explanatory variables, but using only the training data. Okay, I do not want to use at this point the testing data. I'm not touching the testing data yet. So going back to my SAS, here I'm using procreg to fit the model with the training data. So here's my model with my training data. You see that it's y hat equals 1.103 plus 0.462 times high school GPA plus 0.0141 times HU plus 0.256 times weight. So I just wrote that out. Here are my notes. Okay. I just wrote out that model, and I also put it as a comment here in my SAS code. Notice I put it as a comment in my SAS code because we're going to use that. So that's our model for our training data. Okay. And if we look at the results here, is the model significant? Yeah, this model, it looks like it has some predictive ability. The F test is significant. So F is equal to 12.98, p-value is less than 0.0001. So yes, the model is significant. Okay, the model looks like it's probably going to be useful for something. What's the value of the adjusted R squared? 0.235. Okay, so R squared adjusted equals 0.235. And again, I'm using R squared adjusted here because we're going to compare models. Remember, we use R squared adjusted to compare models. So now we're going to run some code that computes the value of the testing MSE, which is really, I'm actually going to calculate the average squared error rather than the mean squared error. I'm going to divide by n rather than n minus k minus 1, just because it's simpler. It doesn't really matter which one you use, but as you'll see, it's a piece of cake to do the average squared error. So if we look at this code that I'm going to run, I'm creating a new data set that I'm calling testing 1. So I'm going to set testing. It brings in the testing data. Remember, these are data that we did not use to create our model. And then I'm going to generate y hat for each observation in my testing data set. For each observation. And note that the way I'm generating y hat is using my model from my training data. So I'm taking the training model and I'm going to create y hat for the testing observations. And then I'm going to calculate yi minus yi hat squared for each of my testing observations. And then I can simply use proc means to get the average of those. Okay. So let me go ahead and do that in SAS. So I've already, this is the same code that's in your notes. If I run this, the ASE, the average squared error of my 101 observations that are in my testing data set, is it supposed to be 101 or 111? Oh, it's supposed to be 101 observations in my, sorry, I made a mistake in my notes. There's actually 101 observations in my testing data, not 111. Sorry about that. So the average squared error in my 101 observations is 0.143. So ASE equals 0.143. We have to keep that in mind. We'll refer back to that. Okay? So now, let's generate similar code to include verbal SAT in the above model. And I already have that set up in SAS, so you can see how I did it. So now it's the exact same model that I fit above, but now SATV is in there. So we can fit that. And the equation for that model is now y hat equals 0.783 plus 0.431 times high school GPA plus 0.0146 times HU, the humanities, plus 0.222 times white, plus 0.00074, 0.000744, I'm going to say, times SATV. Okay. So I just wrote that in my notes. And is this model significant? Yes, it's still significant. So the F is equal to 10.37 with a p-value less than 0.0001. So that looks good. And the adjusted R squared is 0.2427. So I just wrote that out. The adjusted R squared here is 0.2427. That's slightly bigger than we got before. So it looks like SATV might be contributing to our model, right? But if we look at our output, so remember this model is fit only with the training data, and the p-value for SATV is non-significant. It's 0.14, so it's bigger than 0.05, so it's not a very small p-value. So we might be inclined to throw that variable out of the model. But let's see how it does. So here again, this is the exact same model that I wrote out in my notes. I just put it in SAS so I would remember what it was as a comment here. And now I'm going to create this called testing line 2, set testing, and now I'm creating my y hats for the testing data using this more complex model with SATV in there. And I'm also going to create the squared residuals for this model, and then use proc means to get the average squared error. And if we do that, we find that the average squared error for this model is 0.139. Okay, so the ASE for this model is 0.139. Of these two models, which has the smallest MSE, or we're actually looking at the ASE, okay? And what does this mean in terms of how well each predicts the first year GPA with the testing data? So the model with SATV has the smaller average square error. So this suggests that this model predicts better predicts GPA better for the testing data. Again, remember the testing data were not used to fit the model. We're just using those to test the model.